this go down. I see it's a laser. Okay.
Good day, everyone. Good day, everyone. I'm going to present the topic titled Computational Fluid Analysis of Pressure Drop in Advanced Solid Belt. This is research from Morgan State University. All the others are from Morgan State. When we talk about biomass, we know biomass is coming from wood, agricultural waste. And there's been a great demand of how do we turn biomass into energy, which is an aspect of waste to energy. And these are various researchers because biomass is a source of renewable energy. The type of biomass we're using in this literature is what we call poultry waste. And poultry waste is just excrete from chicken waste, which we have here, the chicken waste, and this is poultry litter waste. And this research is about how do we convert this poultry waste into a source of energy. We have some difficulties with poultry litter waste. One of it is the nitrate runoff, which is the process that contains high nitrate like nitrogen and phosphorus, which causes nitrate runoff of the grass. We also have the ammonia emission because it has bacteria, it produces ammonia. We have heavy metal contamination like copper or zinc, and also we have it contains odor. And most times, this waste just like that in farms, and there's been so many comments of having effective waste management to control all of these things. There are various processes which we use. We have the pyrolysis, which ranges from 350 to 600. We have the classification from 800 to 1000. We have the combustion, which is from 800 to 1500. And this research is going to stay on the combustion part of it. There are various types of fluidized belt. We have the fixed fluidized belt. We have the fluidized belt combustion. Under it, we have the bubbling and the circulating fluidized belt. This is circulating, this is the bubbling, and this is the fixed fluidized belt. But for this research, I'll be focusing on the advanced swirling fluidized belt. These are various characteristics of all the fluidized belts, showing how they are in comparison with each other. If you consider the heterogeneous catalytic gas phase reaction, we will see the one that offers the best is the advanced fluidized belt because it can offer for small granular powder conformable catalysts that can handle the scattering of solid. When we look at the heat transfer, also it provides excellent heat transfer for the story. And when you look at the particle size, it provides for more particle size. So that's why we are studying this. These are showing the various problems of fluidized belt, incomplete combustion efficiency, environmental emission, and heat transfer. But we are looking at how we're going to improve heat transfer. For this research, we're using computational fluid dynamics analysis. There are various models, but the model which we're using is the Ilaria model, which considers an inhomogeneous model. This is just showing us a little background of the Ilaria model, which we're using ANSYS fluid flow analysis. These are some equations showing us the phase composition, the volumetric, and we have a continuity equation which is being inputted and which we use in our model. This is just showing us the various parameters which we indicate to use to solve all our model. Okay, this is actually in the KSET lab, but because of that's why we're making it so small to use. This is actually the model which we have in our lab, which we are working on it, and also trying to build up the geometry of it. You can see the waste is coming in from here. You can see the geometry of the representation of it. And this is showing us the full geometry, which we have everything here coming in. The waste is coming from here, the primary air is coming from here, the secondary air is coming from here. And this. One of the good things is that it's just not just one air coming in. We're having a secondary air coming in, and they are coming in swirling form. Means they are coming in tangential into the thing to help with the flow of the heat. So, okay, this is showing us being the CFD constraint, which will ban the primary air and as well as the secondary air, and this is the outlet. This is showing us where the potentiometer is coming from and where the natural gas is coming from. Okay, in our simulation, because we have the experiment, we want to make sure that what we are modeling is different. We have the primary air flow is 250 cubic feet per minute, but we convert it using our volumetric flow rate because we want to use our mass flow rate in our analysis. And the secondary air, this is the rate, because they are 4 of it. There are 4 of it, which we have here, going tangentially for places 1, 2, 3, 4. So as a result, we'll divide this by 4, making it 100. So for our analysis, each of the phases we have this coming here, the natural gas air and the potentiometer, as well. The boundary condition was stationary wall and no slip condition. For our analysis, we did some parametric analysis. For this, we are generally considering 3 parameters: the sand mass, the primary air mass flow rate, and the potentiometer mass flow rate. And we want to know the impact on the pressure drop, because the pressure drop affects the heat transfer a lot. And ability for you to know which parameter increase the flow of the pressure drop is going to help in the effective flow of how far the heat transfer is being generated. This was a result which we found out that when we increase the sand mass of the bed, the pressure drop tends to increase over time, which shows that, okay, so our thing is moving and the bed is being fluidized and there's effective mixture of the process. We also were able to check that the primary air mass flow rate, as we told, because the air flow rate is the one blowing it from down, making it to be fluidized, also increases. But we found out that even you increasing the potentiometer flow rate, increasing it from when we have R1 and this, it's increased. But when we go down, it decreases. So it's not about the amount of you feeding. Why? Because the more you feed the potentiometer, and if it is being born and there is no effective combustion, even though you keep increasing it, and there is an incomplete combustion, enough heat will not be transferred. So the main objective is, no matter what you are feeding into it, we need to ensure that we have a complete combustion and not an incomplete combustion. This is just showing us the various. We try to plot the control of the product. This is just showing all the CO2, and this is showing us the water that is being generated. And as we can see here, this is showing us the various control lines. So as a result of this research, we are able to find out that pressure drop is greatly affected by the sand mass and the primary air. There's no much significant effect, even though when you start increasing your potentiometer flow rate. It's better you maintain a steady one and ensure you have a complete combustion. The pressure drop is directly related to the potential quality of the bed. I will also found out that the pressure drop in the fluidized bed combustion is a key parameter that affects the efficiency, stability, and operation. Sorry, since my hand is too fast. And the operation cost of the system. And proper monitoring and control the pressure drop are essential to achieving the optimal performance in the fluidized combustion. These are some of the references we use, and I want to say thank you for the time.
Yes. Thank you for that. Any questions from the audience? This is beyond my field, but I have a quick question about monitoring the pressure. Should this are there a automatic system that could do that in whatever your reactor design?
Yeah, this is a simulation, so to help us monitor it. So now, what we are monitoring now is the temperature, because we have temperature sensor which can read the temperature. Also, we also have some flow meter that will show the temperature reading. So I did this simulation so that we can now, because it's an NSF project, so we're kind of saying of device will be buying, because it's atmospheric. We can measure the air outside, or we need to start measuring. So we are working on that to get equipment that help us in measuring the pressure. So this is just a simulation.
Thank you.
Yeah, you're welcome.